Hi, everyone. Thanks so much for coming this evening. Thanks for such a kind introduction. I'm going to tell you a little bit about this new book, which is on the screen at the moment, How to Expect the Unexpected. It's about predicting the future. It's about making better decisions, but it's about learning from mistakes that were made in the past and recasting those mistakes as lessons for us to take into the future, including sort of tips and tricks and things how you can, ways you can make your life a little bit better, perhaps, and you can avoid making the same mistakes that people have made in the past. But to warm up, I like to do a little section called School Reports, because I see there's some young people in here. And so the game is, basically, I'm going to give you a quote from someone's school report, and I want you to guess who that quote was about. So here's the first one. This one's about PE, or physical education. He must devote less of his time to sport if he wants to be a success. You can't make a living out of football. Any ideas who that could be? Just put your hand up if you've got a clue, if you fancy a guess. Yes, sir.
Marcus Rashford.
That's a really good shout. It's not Marcus Rashford. It's a really good one. One more, yeah?
David Beckham.
David Beckham, that would be equally appropriate. It's actually Gary Lineker, so you are exactly on the right lines. It is a famous footballer who, Gary Lineker had a stellar career. He won the Golden Boot at the Mexico '86 World Cup. He is the BBC's best paid presenter, not just sports presenter, but best paid presenter. So that teacher did not make a very good prediction. Gary definitely did make a good living, or does make a good living out of football. How about this one? This one's English. A persistent muddler. Vocabulary negligible. Sentences malconstructed. He reminds me of a camel. Anyone got any ideas about this person? Who this could be? Yes, sir.
Boris Johnson.
Boris Johnson, that's brilliant. He reminds me of a camel. Very interesting. No, it's not. Yes, sir.
Donald Trump.
Donald Trump. Well, populists. No, this is in fact Roald Dahl. And it's really interesting that it's Roald Dahl because obviously he made his living from writing brilliant children's books, but also this idea of being a persistent muddler, he's quite famous for his gobblefunk, right? These words that he made up, the BFG uses words like whiz poppers and frobscottle, words which weren't in the English language, which describe the things he's trying to describe really nicely. And actually, the astute amongst you will have noticed that this actually isn't a picture of Roald Dahl. This is Hugh Bonneville playing Roald Dahl in a recent biopic, and this is a picture of the real Roald Dahl. There's going to be a theme here, so stay with me. All right, so you've got the idea. The school reports are not very accurate. So here's another one. Science. He will never amount to anything. Anyone want to have a go at this one? Yes.
Einstein.
It is Albert Einstein, yeah, probably the most famous scientist of the 20th century, if not all time, Albert Einstein. And again, the astute amongst you will notice that this is not actually Einstein. This is Geoffrey Rush playing Albert Einstein in a recent biopic. This is the real Albert Einstein. Okay, so last one now. This one's about maths. This is my subject. Not very good. He spends a good deal of his time apparently in investigations in advanced mathematics to the neglect of his elementary work. A sound groundwork is essential in any subject, and this is a really harsh ending to the report. His work is dirty. Any ideas about who this could be?
Is this yourself?
No, it isn't. I never got to advanced mathematics when I was at school, I don't think. Any other ideas? One more guess, anyone? Andrew Wiles, a good shout, a very famous mathematician. It's not actually, it's our code-breaking World War II hero, Alan Turing, an incredible mathematician, father of computer science, father of artificial intelligence, father of my own subject, mathematical biology as well. And again, the astute amongst you will have noticed that this is not Alan Turing, this is actually Sherlock Holmes. No, sorry, it's not Sherlock Holmes, it's of course Benedict Cumberbatch, and this is the real Alan Turing from his days at school. Okay, so the reason I like to start with this section is because these are some examples of teachers not making very good predictions, but also to say to younger people in the audience that you shouldn't be defined by what someone else thinks. This is the first take-home of the talk. Don't let someone else's opinion define your future. Because I think we think of teachers as, well, they're people that convey facts to us, aren't they? And we tend to take everything they say on trust, including their opinions of where we're going to go in the future. But actually, if a teacher says to you, you're not very good at maths or you're not very good at English, I would say say to you, don't take that to heart. Don't say that you will never write a book. I was not very good at English at school. I did enjoy maths. But, I've ended up writing a book. So, it can happen. And so, don't take these things to heart. Don't let someone else's opinion define your future. Okay, so into the main meat of the talk. In the book, there are basically two main themes, two main ideas that I want to get across, two things that can sort of scupper us when we're trying to predict the future. And those two things are non-linearity and randomness. Okay, so I'm going to cover both of those topics. The talk's going to be roughly split into two parts. And I'm going to try to tell you a little bit about both of these things, where they can trip us up, what they mean, and how we can get the better of them. So firstly, non-linearity. I've said the word non-linearity 3-4 times now. I don't know if people even know what it means, so I'm going to explain what it means. And to explain what non-linearity is, I need to actually explain what linearity is, okay? So if two variables vary linearly, it means that a fixed change in the input gives you a fixed change in the output. Okay, so that's quite a lot of words there. Let me show you a graph. Let's imagine that we are converting pounds into New Zealand dollars, okay? Roughly the exchange rate is about $2 to £1. So if I draw you a chart of the number of pounds on the horizontal x-axis at the bottom and the number of dollars you would expect to get back from that number of pounds, it looks like a straight line. This is why we call these relationships linear, okay? So for £20, you get back 40 New Zealand dollars. If I increase the amount of pounds I want to change by a fixed amount, so up to £40, then the amount of dollars I get back increases by a fixed amount. It increases by $40. And the same way, when I increase again from 40 to 60, so another increase of £20, the output again increases by another $40 from 80 to $140, to $120. Gosh, my math's right. Okay, so this is the essence of a linear relationship. A fixed change in the input gives you a fixed change in the output. Now, this particular relationship is a special type of linear relationship. It's called direct proportion. And it's a very special line because the line goes through the point 0, 0. That is to say, for no pounds, I get no dollars in return. And this very special relationship means that when I double the input, then I also double the output. Okay, so if I jump from £20 to £40, if I double the input, then I should double the output as well. I go from $40 to $80 in the output, okay? But not all relationships that are linear are in direct proportion. Some relationships are not. So for example, there are two main temperature scales that we use in the world. When I say we use in the world, I mean that everyone uses Celsius except for the Americans who use Fahrenheit, okay? So there are two temperature scales that we use, and we can convert between them. And the rule is that you take your temperature in Celsius, you times it by 1.8, and then you add 32. Okay, it's crazy, I don't know why, but that's the way, it was defined from different boiling points of water. Well, for Celsius, it was defined as the freezing points and the boiling points of water, but for Fahrenheit, it was something to do with the boiling points of brine or salt water or something like that. Anyway, so it's a strange scale, but every degree of Celsius is worth 1.8 degrees in Fahrenheit. That's all you need to know, really, and this is what the relationship looks like. It doesn't go through 0, 0, so it's not direct proportion, but it is still a straight line. So this time, if I take 10 degrees Celsius to work out the Fahrenheit temperature, I times it by 1.8, I then add on 32, and I get to 50 degrees Fahrenheit. If I increase the input by a fixed amount, say 10 degrees, then I should increase the output by a fixed amount. In this case, it'll be 18 degrees, because remember, every degree Celsius is worth 1.8 degrees Fahrenheit. So I get 68 degrees, and if I increase it by another 10 degrees Celsius, then I get another 18 degree increase in Fahrenheit. So a fixed change in the input gives me a fixed change in the output. But this time, if I double the temperature in Celsius, I don't double the temperature in Fahrenheit. So if I double the temperature from 10 to 20 in Celsius, then I don't double the temperature from 50 to 100 in Fahrenheit. It goes up by this fixed amount. So I've laboured this point a lot now. I've gone through this for the last 5 minutes. Everyone's getting bored about linear relationships. But this is sort of the point. Even though you might not know the definition of a linear relationship, we are so familiar with them because we use them all the time. We are taught them from the earliest days in school because these are the sorts of questions that we get in school. So here's the question. If Jane pays £5 for 10 grapefruits, how many grapefruits does she get for £50? Does anyone want to have a go at this one? No pressure. If you don't want to have a go, that's fine. I understand there's a lot of, it's a high pressure situation. Anyone fancy? 100. Yeah, 100 grapefruits, exactly. So that's exactly the right answer. If you spend 10 times as much money, so £5 to £50, you should get 10 times as many grapefruits. You should get 100 grapefruits if you've got 10 for £5. So maths is this weird place. It's the only place in the world where you can buy 100 grapefruits and no one bats an eyelid. Everyone's like, yeah, it's a really normal thing to do. Of course, what is Jane going to do with 100 grapefruits? She's going to eat them all herself? No. So it's a bit of a strange one. But we also, we're used to this. We know that that's the right way to answer this question because we're so used to doing that question, but we don't stop to think. If you're going to buy 100 grapefruits, you're probably going to get a discount because you're buying in bulk. That's how the real world works. But in maths, that doesn't happen. Everything is linear. But it can trip us up because we get so used to using these linear relationships. So here's another one. This is called a pseudo-linearity problem because it's supposed to trick you into using linearity when it's not the right thing to do. So Laura is a sprinter. Her best time to run 100 meters is 13 seconds. How long will it take her to run a kilometer? And I'm not going to ask you to do this one. I'll go through it with you, though. So a kilometer is 10 times as long as 100 meters. So using our linear argument, it should take her 10 times as long. It should take her 130 seconds, which is 2 minutes and 10 seconds. But there's obviously a problem with this, right? Does anyone recognize this person? No, it's actually Noah Ngeni. He's a Kenyan athlete, and he's the world record holder for the kilometre. It's not a very often run distance, but there is a world record for it. His world record time is 2 minutes and 11 seconds, right? So we're saying that Laura, who can do 100 meters in 13 seconds, can break the world record just because we've scaled it up linearly. But obviously it doesn't make sense because no one can keep or sustain their best 100 meters time over the course of a kilometer. But again, we're so drilled in, we're so used to using these linear arguments that sometimes we don't stop to think about whether the answer actually makes sense. 2 minutes and 10 seconds can only ever be a lower bound on what Laura can do for the kilometer. So that's another example where people tend not to think, and we're so ingrained with this idea of linearity that we just use it without thinking. Here's another one. If it takes 3 towels 3 hours to dry on the line, how long does it take 9 towels to dry? So I asked this to ChatGPT, the AI chatbot, which is designed to mimic human interactions, and this is what it said. It said, if it takes 3 towels 3 hours to dry on the line, then it would take 9 hours for 9 towels to dry. And it gives this reasoning. It says, it uses the correct reasoning because the drying time is directly proportional to the number of towels. If you double the number of towels, then you should double the amount of time it takes. And if you triple the number of towels, then you should triple the amount of time it takes. Clearly, if your line is big enough, it shouldn't take you any longer to dry 9 towels than it takes to dry 3 towels. But maybe this is the expected behavior for ChatGPT because it's trying to mimic human behavior, human interactions. And actually, I think if you asked a lot of people, that's maybe the answer that they would give. Because again, we're so ingrained with this idea of linearity that we don't stop to think that actually, in this case, the relationship is just constant. It doesn't matter how many towels you're drying on the line. It takes the same amount of time as long as you've got enough space on your line. Okay, so that's another example. One more. So this one that you might actually be able to answer mathematically. So Farmer Jones takes an hour to mow a square field of sides of length 100 meters. How long would it take her to mow a square field with sides of length 300 meters? So the linear argument says, well, the field is 3 times as long now, so it shouldn't take 1 hour, it should take 3 hours, right? So the linear answer is 3 hours, but that's not the correct answer. Because of course, when you're mowing a field, it's not the length of the side of the field that counts, it's the area of the field that counts, right? And the area scales as the square of the increase in the length. So if the length increases by a factor of 3, the area should increase by a factor of 3 times 3, or the square of 3, by a factor of 9. So it should take her 9 hours to mow this field. And so it's something that you can answer with math, but again, when set this problem, the majority of school students and indeed adults who set this problem will answer in the linear way and will say it takes 3 hours because they just do this linear scaling without thinking too hard about it. So this is an example of a relationship. So all these questions are a little bit contrived, perhaps, right? They're all the questions you might see in school, but they're not really real-world problems. So where can you use this in the real world? Well, pizza is where you can use this in the real world. And this is really useful because I think this can be counterintuitive. So here's a question for you. If you want to maximize your value for money, is it better to order 2 8-inch pizzas for £10 or 1 16-inch pizza for £20? And the answer is a bit surprising. Again, the linear answer is it doesn't matter. okay? Because two 8-inch pizzas, you've got the same 16-inch diameter as a 16-inch pizza, and you're paying £20. So you're paying £20 for 16 inches of diameter, and you're getting 16 inches diameter with the £20 16-inch pizza, so it's the same. That's the linear answer. But of course, that's not right, because what we care about with pizzas is not the total length when you stack them back to back. It's how much pizza you get in your belly, right? It's how much area there is for these pizzas, okay? So actually, here's the 16-inch pizza, and here's the two 8-inch pizzas, okay, overlaid on top. Yes, they do have the same width in total, but they don't have the same area. If you want to have the same area, you need 4 of these 8-inch pizzas in order to get the same area. So you need to pay £40 rather than the £20 that it would cost you to buy the 16-inch pizza to get the same amount of area. And so I suppose the lesson is that you should buy the biggest pizza that you can, which suits the needs of the people who you're buying pizza for. So there's another little subtlety in here which I've sort of swept under the rug, which is, does the price of pizza actually vary linearly with the diameter? Because I said an 8-inch pizza was £10 and a 16-inch one was twice as much. That was £20. Is that true? Well, actually, it turns out that it is quite true. This is a genuine linear relationship. So there was a journalist called Quotrung Boy, and he worked for the New York Times, and he was sent out on a mission. He went to over 4,000 pizza parlors, and he found 70,000 different prices of pizza. And here they are. I've reproduced the plot here. And he fitted a line, a curve, and the best fit curve was a straight line. So it's not perfect, obviously, but roughly the price of a pizza scales linearly with the diameter of the pizza. But remember, of course, that the area of the pizza scales with the square of the diameter. So you get better value for money. You get more pizza, more bang for your buck, the bigger the pizza you get. So get the biggest pizza you can, obviously, that suits the needs of the people that are eating the pizza. All right, good. So that's a little bit about linearity and where some simple non-linear relationships can confound us. Another non-linear relationship that confounds us is when we encounter things like positive feedback loops. So what's a positive feedback loop? It's when a quantity causes itself to increase or indeed to decrease. Okay, so let me give you some examples. The most simple example that most people have heard of is acoustic feedback. Okay, so this is Jimi Hendrix, and he was a massive proponent of feedback. In fact, his music is basically synonymous with feedback. And what happens with acoustic feedback, you'll remember, you get this ramping up of volume. It sometimes sounds like high-pitched notes, someone's scratching their fingers down a block. It's uncomfortable. You want to sort of shrink away from it. And basically what's happening is the microphone is taking in a sound and it's passing it to the amp. The amp is then increasing the volume of that sound, passing it, and the mic is then picking it up again. So if the mic's too close to the amp, this happens. The mic then feeds it back to the amp sends it out again, the mic picks it up again, and it tends to highlight certain frequencies. It's usually associated with high frequencies, but it really depends on the quality of the mic and the amp. You can do it with different frequencies, but you get this sort of spiral where the sound, the volume gets sort of out of control. So that's a sort of relatively benign example of feedback, but actually it can have much more serious consequences. So if you try to go to the region of Himachal Pradesh in northern India during monsoon season, you will be advised against it. And the reason is because in that region during monsoon season, they have lots and lots of rock slides. What happens basically is that the monsoon rain, the heavy rain, can dislodge small bits of soil. Soil can maybe hit and dislodge a pebble. A pebble then hits a stone. Stone hits a rock, which hits a bigger rock, which hits a boulder. And it ends up sending hundreds of tons of rock streaming down the mountain and basically squashing everything that gets in its way. So you're advised not to go to these regions during monsoon season, because that's particularly when the ground becomes unstable and you're more likely to have these rock slides occurring. So that's a sort of more serious example of where positive feedback loops can occur. You also get positive feedback on the stock market. So maybe a stock price is doing quite well, a company's done well, and the stock price rises a little bit. And people see that rise in the stock price and they think, oh, I'm going to have some of that. So they get in there and they try to buy the shares. But that means that the demand is outstripping the supply. So the people who've got the shares can say, well, I'm going to ask for more money for those shares. So the price of the stock goes up. And people see the price of the stock going up again, and they're like, oh, I'm going to have some of that. And they get in and they try and buy some stock, and the demand outstrips the supply again. And it keeps on going up, and you get this spiral where the increase in price in the stock causes the price to increase. And so you get what's called a bubble, right? So you get this bubble where the price of the stock keeps rising and rising, and it rises out of proportion to the quality or the performance of the company. You get this bubble, and the problem with bubbles is, of course, that bubbles burst. Okay, so eventually people figure out that this price of this stock is way above where it should be, and then people dramatically try to sell. So this sort of highlights the fact that actually positive feedback loops, in the three examples I've given you so far, have caused a quantity to increase, be that the volume of a sound or the amount of rock coming down a hillside or the price of a stock. But actually positive feedback loops can cause prices to go down as well as up. You'll get that warning if you ever invest in the stock market. The value of your investment can go down as well as up, and positive feedback loops are no different. So actually, if a stock price doesn't do very well one day, then people who own that stock will be like, oh, I want to get out of this. I want to sell my shares before they go down any further. So that means that then supply is outstripping demand, which means that people who are buying them can say, well, I'm not going to pay that price for them because there's loads of people selling them. So actually, I'm going to ask for a lower price, and the price goes down again. And when the price goes down again, more people try to sell their shares, and that means that this price spiral continues. And again, it can completely crash the value of a company, even though the company is perhaps stable. And we saw that in the UK with the bank Northern Rock. There was a run on the bank despite Northern Rock potentially being savable. People lost confidence, and we went into this positive feedback loop, but a positive feedback loop with negative consequences. One of the most important places where positive feedback loops can play a role at the moment, and why you will hear climate scientists saying we're really concerned about the rises in temperature that we're seeing, is anthropogenic global warming, so human-made global warming. And the worry is there are feedback loops which we may not be able to control after a certain rise in temperature. So, for example, there's a feedback loop called the ice albedo feedback loop, which the albedo is basically how much heat energy the Earth is able to reflect back from the sun back into space. And the more white area, the more light area there is on the Earth, the higher the albedo. The light or white material reflects better than dark material. And the more dark material, so land and sea there is, then the less heat energy that can be reflected. So you can sort of see where this is going. If we make the temperature of the Earth rise, we melt some of the ice. That means the albedo is lower, so we're reflecting less of the heat energy out into space, and the temperature in the Earth increases. That melts more ice, which lowers the albedo again, which means we retain more heat energy, and they're in a positive feedback loop where we may not be able to stop the rises in temperatures that have been caused by an initially perhaps small rise in temperature caused by greenhouse gases, for example. But again, this can work the other way. So there is a hypothesis which suggests that the Earth was once entirely covered in snow and ice for a period of time, because the opposite thing happened. The temperature dropped a little bit, which meant that ice coverage increased, which meant that more heat energy was reflected, which meant the temperature dropped more ice formed, and you got this what's called the snowball Earth hypothesis. So the Earth was covered entirely, apart from maybe a small band around the equator, in snow and ice. And this name snowball Earth is doubly fitting, both because it looks like a giant snowball, but also because these positive feedback loops are often called snowball effects, right? You get a small amount of snow starting at the top of the mountain, it rolls down, and it causes the amount of snow to increase as it goes down the mountain, and you end up with an avalanche. So it's a doubly fitting name. And actually, maybe one of the most pertinent examples of positive feedback loops that we've seen in recent years is in epidemics. Okay, so this is SARS-CoV-2, the coronavirus, that we've just lived through the acute phase of this pandemic. At the start of a pandemic or an epidemic in a particular country, the number of cases, the number of people who are infected, grows as a positive feedback loop. In fact, it grows in a very special way called exponential growth, and we'll talk about that in a second. So the initial phase of an epidemic is subject to a positive feedback loop. I don't know if you remember at the start of the pandemic, 3.5 years ago now, scientists, mathematicians were sort of thrust into the limelight to explain what the hell we were doing and how we were modelling the way that the epidemic was going to go. This was us trying to predict the future. And I'm a mathematical biologist, so I did a little bit of mathematics communication, and I was asked to go on the radio, on the TV news, almost every week to explain basically one number, the reproduction number, the R number, which became very famous. The R number is the number of people that each infectious person will pass the disease onto during the course of their infectious period. So if that number is below 1, then the disease will tend to die out, because each infectious person is not passing it on to enough people to sustain the epidemic. But if it's above 1, then that disease will tend to take off. So at the start of the COVID pandemic, the type of virus that we had, the Wuhan variant, as it's sometimes called, had a basic reproduction number of about 3. So each person that was getting infected was passing the disease on to 3 other people. So that means that the first person that gets infected passes the disease on to 3 more people with this reproduction number of 3, but then the next person, or those 3 people, then pass it on to 3, so you've got 9, and the next layer, they all pass it on to 3 more people, so you've got 27, and you can see how this is growing in proportion to its current size, so this is exponential growth. So we hear the word exponential all the time in the news. People use it as a byword for big or fast, but it doesn't always mean big or fast. Sometimes, like at the start of an epidemic, cases can grow seemingly quite slowly. It can look quite flat. But when something grows in proportion to its current size, that is the definition of exponential growth. But this is what the graph can look like sometimes. We often call it a J-shaped curve because it can look quite flat initially. It can look like it's growing, maybe we think it's growing linearly. It's growing a little bit, but actually, eventually it will grow much, much faster and it will grow out of control. And that's the idea behind exponential growth. So there's a problem in that we don't really understand exponential growth very well. We don't understand exponential behavior very well. We're not really taught it very well in this country, in school in particular. And so a lot of people exhibit what's called exponential growth bias. So this is when we tend to underestimate how big or how large a quantity will be in the future because we don't really understand how quickly exponential growth can take off. So this is the graph I like to use to sort of illustrate this. The black curve is something that's genuinely growing exponentially. The dashed curve is what we think is going to happen. This is our sort of linear expectation of what's going to happen with this quantity. So this exponential growth bias can cause us a number of problems when we come to predicting the future. So one of them is that we don't save enough for the future because we underestimate the rate of growth of our savings. So when you put money in the bank, you get interest on the interest that you're earning. You get compound interest, which means that your money is growing in proportion to how much money you've got in the bank, so it's growing exponentially. Okay? If you leave it in there long enough, then it will grow exponentially. If you keep taking it out, obviously, you can't expect it to grow exponentially. But so we underestimate the value of our savings because we underestimate how quickly exponential growth can take off, and we think things are just going to grow linearly. Similarly, we take on more debt than we should do because, again, we underestimate the value that debt is going to cost us in the future because we underestimate the rate of exponential growth. This is the people who are subject to exponential growth bias. So it means that we take on more debt and we save less. And actually, there's been studies to show that people who exhibit higher levels of exponential growth bias have higher debt-to-income ratios, so they have more debt compared to their income than people who understand exponential growth better. And the other place where exponential growth can really stymie us, not just the individuals that don't understand it, but everyone, in fact, is when we're trying to control an epidemic. Okay, so people who exhibit exponential growth bias, there was a study done in 2020 near the start of the pandemic suggesting that people who exhibit exponential growth bias were less likely to undertake measures which were designed to suppress the spread of the epidemic. So less likely to wear masks, less likely to social distance, less likely to quarantine or isolate, and less likely to stick to many of the other rules that were designed to do contact tracing and so on. And that stymies all of us, right? It doesn't just stymie them because actually trying to control the pandemic is a collective effort. So actually, I would argue that if we got people to understand exponential growth better, then we might be better able to control a pandemic or at least an epidemic in our country. Okay. So that's the end of the non-linearity part of the talk. There are loads more examples in the book of where we get positive feedback loops, negative feedback loops, things like self-defeating prophecies, self-fulfilling prophecies, backfirings, something called the Cobra effect. I'm not going to tell you what it is, but you can look it up in the book. It's all sorts of places where non-linearity can confound our expectations because we have this thing called normalcy bias, and we tend to think that things are just going to carry on as they are, or to at least keep changing at the same rate that they are. And when that doesn't happen, that can really upset our expectations. Okay, so the take-home messages are we are predisposed to expect linear relationships, but most, perhaps many at least, but a large majority of the phenomena we encounter from day to day are not linear phenomena, right? Not every relationship is linear. So we need to look out for these non-linear relationships. We need to look out for exponential growth. We need to look out for this square rule, which governs how much pizza you get for your money. We need to look out for cubic laws, which tell you how a volume changes as a length changes. And we need to look out for feedback loops, positive and negative. We need to look out for chaos in the weather forecast. Non-linear behavior is everywhere. Okay, so that's the first set of take-homes. In the second part of the talk, I want to tell you about randomness and how good or bad we are at being and seeing randomness. So I'm going to start with this diagram here. So I've got 3 sets of dots. Each diagram, A, B, and C, they all have the same number of dots in them. One of these diagrams I have generated on a computer using a random number generator. So what I've done there is I've taken a position, for each of the points, I've taken a position on the x-axis, on the horizontal axis for the point, and I've chosen that uniformly at random, so with equal probability anywhere across the bottom of the axis. And I've done the same for the y-coordinate for that point. So I've chosen the y-coordinate with equal probability to be any coordinate from the top to the bottom. So I've generated 230 odd points, and I've generated them using this uniform random numbers. And so I do want to get a gauge if you feel brave enough to do it. I'm not going to ask anyone specifically, but I want to see a show of hands, if you don't mind, to see which one we think is the genuinely randomly generated data set and which ones aren't. Okay, so who thinks that A is the genuinely randomly generated data set? Okay, so maybe a third of people, perhaps? What about B? Who fancies B? So yeah, similar, maybe slightly more for B. And what about C? Yeah, a few people, not quite as popular, but yeah. So I think B was roughly the most popular. Some people went for A. Let me tell you what these data sets actually represent. So C, this is the nesting sites of Patagonian seabirds. Why did I choose this one? Well, these Patagonian seabirds are very territorial, right? They like to lay their nests not too close to the others. They like to lay them in one place because it's good for them to lay their eggs there, but they don't want to be too close. So they actually like to stay a long way or as far away from each other as possible. And actually you can sort of see that reflected in the pattern itself. You can see it's almost grid-like, okay? But actually we think of randomness as being well-spaced. So for the people that went for C, I can totally understand that because we think, I even described when we were generating the positions of the points, saying it was equally likely to be anywhere along this point, which gives us this idea that randomness is evenly spaced. And in fact, it generally isn't. What about B? So B is actually the nest sites of ants in a field. So these ants also don't like to be too close to each other. So you can see they're quite well spaced, but they don't have the same overarching view of what's going on as the seabirds do. So sometimes they build their nest a bit too close to each other, but generally they find that out and they move their nest. They don't like to be too close to each other. So obviously it turns out that A is the genuinely randomly generated data set. And I'm going to talk about why some people went for A and some people didn't. But in particular, those people that went for B, I think there's another thing going on, which is maybe not to do with the points themselves, but it's to do with something called middle bias. Okay, so we exhibit this bias. We don't really often know that we're doing it, but when we genuinely don't know the answer to a question, we tend to plump for the middle option. Now, this is a weird phenomenon, but we tend to think the outside options are not going to be as likely as the middle ones. So we do this in standardized assessment tests. So when students genuinely don't know the answer to multiple choice questions, they go for B and C more than they go for A and D, okay? It's a real thing. There have been studies to test this. We do this in the game of Battleship, right? If you don't know the game of Battleship, you've got some ships to place on a grid, and your neighbour does the same, who you're playing against. You can't see each other's grids, but you have to guess where their boats are and try and sink their boats by guessing in the right coordinates. We tend to guess, when we're guessing, we tend to guess the middle coordinates more than the ones around the edges. Now, yes, there are more middle ones than ones on the edges, but even accounting for that, we tend to guess the middle points disproportionately frequently. So if you're playing battleships, think about placing your ships around the edge, because that might give you the advantage in the game. This one's a bit weird. We tend to apparently choose the middlemost toilet cubicle rather than the edge ones. And I used to tell this anecdote and say, don't ask me how they found this out, because that would be weird. But I actually went back to the paper and found out how they do this. And they don't put a video in there or anything like that. They don't even survey people. They ask the janitor how often he replaces the toilet rolls in the cubicles and use that as a proxy for how often people are using them, which I think is really clever. Anyway, so apparently we even have middle bias when it comes to toilet cubicles. really importantly, when you're making a decision about maybe like when you're buying insurance and you've got several options, you often get faced with a basic option and a standard option. And most of us, when we're faced with that, we'll be like, well, the standard option isn't giving me that much extra, and actually it's $180 more, so I'm probably going to go for the basic option, okay? But this isn't what we're usually faced with, right? We're usually faced with this. Right, we've got the deluxe option, which is so expensive that it's unfeasible to do it. And it doesn't give you that much more than the standard, but we're like, well, that's too expensive. But I don't want to be a cheapskate. I'm not going to go for the basic option. Standard option will do me, because it's standard. I'm standard. It's fine. I'll take the standard option. So they get us to bump up. You know, they were never going to offer us the deluxe. No one's going to buy the deluxe option, but they put it there so that we exhibit this middle bias. So be aware of that. Are you really getting anything extra out of the standard option over the basic option, or are you just scared of looking like a cheapskate, right? So think about choosing the basic option, I think, and be aware of this middle bias. And we'll come back to this again in a second. So going back to these randomly generated data points, the reason why I think some people don't go for A, and well done if you did go for A, you got it spot on, but I think the reason why some people don't go for A is because it looks like there's patterns. It looks like there's clusters in there. And we think randomness is well spent. You couldn't have possibly randomly put 5 dots on top of each other, overlapping each other, could you? That doesn't seem very random. And there's also big areas where there's no dots at all. Like, that's not very random. Surely there should be dots, roughly everywhere. That doesn't feel very random to us, okay? So I think this is why some people don't go for this option A, because it looks like clusters. And actually, we're very good at spotting clusters, and so this may be sort of apocryphal story, but the sort of story goes that when we were hunter-gatherers out, hunting, we were, always aware of potential predators coming to eat us. And so we hear a rustle in the bushes behind you. It might have just been the wind, but it might have been a tiger. So you run away from the rustle in the bushes and you survive, okay? It might not have been a tiger, but you run away and you survive and you get to pass your paranoid genes on to the next generation. So we've got very good at spotting patterns when they're actually maybe not patterns at all, and maybe they're just randomness, maybe they're just noise. And actually we use this nowadays not in hunter-gathering, but also when we're thinking about food. People tend to use it to spot Jesus in pieces of toast. Now this one is actually quite a hard one, so I've zoomed in on it, and there you can see it now, right? This is a beardy bloke, and obviously because it's a beardy bloke, it's not me, it's the one everyone knows, and actually some people think that this is, actually a sign from God that, he's decided to visit upon you Jesus in the form of a tortilla, in the form of a wrap. And so this is a phenomenon called pareidolia, where we spot things that we think we recognize even where those patterns are actually just randomly generated. This is pareidolia, and it's a sub-phenomenon of something called apophenia, which is where we don't just spot the pattern, but we then think there's a causative mechanism behind it. We think God has put Jesus' face in the toast, or here, this is the red face of Mars. This is a picture of some craters and some hillocks on Mars lit by a particular angle of the sun, and it looks a bit like a face in shadow, lit from a particular angle. And people have spotted this face and said, oh, this is evidence of life on Mars or extraterrestrials or whatever it is. And of course it's not. It's effectively just a random pattern on the surface of Mars, but it looks a bit like a face, and we've recognized it as a face because we're good at recognizing faces. Again, it was important for us to recognize faces in the past so we could quickly judge when we came upon someone what their emotional state was, whether we needed to fight this person or run away from them or something else, whether they were friendly. So we're good at recognizing faces, but we're also very good at drawing conclusions where they are not warranted. And actually one of the main messages in the book is that coincidences are incredibly unlikely. If you're given enough opportunities, even incredibly unlikely things can happen. Someone wins the lottery most weeks, right? Even incredibly unlikely things can happen. If you look at enough tortillas, then eventually you'll probably find the face of Jesus in one of them, right? That's well, that's not the main message from the book, but yeah, coincidences can be surprisingly likely. Let's say it like that. Okay, so another example of where this has happened is in iPod Shuffle. So this is a now obsolete piece of technology. For some of the younger people in the room, you won't know what this is. Why would you? But this was a device that you could upload all your music to. So you could get like 10,000 songs on this device, and you pressed play at the start of every morning, and it would randomly shuffle through your songs without repeating them throughout the day. This was good because it meant that you didn't just go to the same old music that you always went to. You could listen to all of your music and really get the most out of it. Now, there's a journalist called Stephen Levy, and he was listening to his shuffle one day, and he listened to a Bob Dylan song, and the next song that came on was a Bob Dylan song. And he said, "What? This is wrong. This is not random." So he was in a fortunate position because he was a tech journalist that he was actually interviewing Steve Jobs. And so he said to Steve Jobs, "Look, I've got this iPod shuffle that you've made." Steve Jobs was the CEO of Apple at the time, for younger people who don't know that. And he said, "This is not random. How could it possibly be random if two Bob Dylan songs came up one after the other?" And Steve Jobs got an engineer on the phone and said, can you just check that the algorithm is genuinely random?" And the engineer said, yeah, it's definitely random. And Steve Jobs told this to Stephen Levy. But nevertheless, Stephen Levy went away and he wrote an article in Newsweek saying, "Well, this happened to me and I don't think it's random." And loads of people got in contact saying, "Yeah, it happened to me. 2 Oasis songs or 3 Manic Street Preachers songs played at back to back. That is not possibly random." And so on the back of this sort of public outcry, Steve Jobs spoke to his engineers and said, "Could you change the algorithm so that 2 songs by the same band do not come up back to back?" And as Steve Jobs described it, he said, we're making the algorithm less random to make it feel more random, to make it conform to our expectations of what randomness is like, which is sort of crazy that our expectations influenced Apple's technology. So I've just tried to explain that we're not very good at spotting randomness. We tend to draw conclusions, false conclusions. We tend to spot patterns where there aren't any. But if we're not good at spotting randomness, we're also very poor at being random. And now I need a help from someone in the audience. I need a volunteer, but I'm going to explain what you need to do before I ask you to volunteer. So don't put your hand up just yet. So what we're going to do is we're going to go to a website which is called an Aronson Oracle. And this is a screen grab of the website. It's going to ask the volunteer to press 2 keys, F and D, as randomly as you can, it says there. And the computer is then going to try and predict which key you're going to press next. So to give you the expectation of what should happen, if you are able to genuinely press the keys at random, the best the computer should be able to do is to predict what you're going to do with 50% probability. It shouldn't be able to do any better than that if you're being genuinely random. I'm not going to spoil and say what happens when I do it. I want a volunteer to come down to prove that I've not fixed it. So does anyone fancy? All you have to do, come down, press 2 keys as fast as you can, as randomly as you can for a little while. Does anyone fancy it? Yes. Who's me? Up here, yeah. Can you make it down? Yeah. Brilliant. Don't jump. Just come down the stairs. That'd be lovely. Yeah, brilliant. Perfect. Thank you. So can we give a nice round of applause to our volunteer, please? Brilliant. We'll just wait for a second while our volunteer comes down. Shout me your name while you come down. Chris. Brilliant. Thanks, Chris. Okay, come down as fast as you can, Chris. Don't trip though. Come down quickly. That would be unexpected, and that would not be a good end to the talk. So we're going to get Chris down here. I'm going to get him to stand in front of my laptop. I'm going to get the website up while we're waiting. So hopefully, if I press this link, it should take me to the website. Good. And so Chris is just going to press the 2 keys, F and D. He's going to try and do it as randomly as possible, okay? And we'll see how well he does at being random. Actually, I found when I've done this before that kids tend to be better at being random than adults do. So hopefully, Chris, hi. Let's give another round of applause to Chris, please. Thank you so much. Chris, come up here, mate. So what I'm going to ask you to do is just to press these F and D keys. We're going to try and get through maybe 100 presses, so we're going to do it quite quickly. But you want to do it as randomly as you can, if possible. So what's going to happen is, after you've pressed it 5 times, it's going to start making predictions on the screen, so everyone should be able to see it, hopefully. A red is a wrong prediction, and if it's just white, then it's a correct prediction. And then after 25 presses, it's going to start outputting and telling you how right it's doing. So it should give us a percentage, and if that percentage is above 50%, then it's being able to predict better than we would, it should be able to if it was purely random. So F and D, if you want to put your fingers on there, and just, go for it. Okay, so it's starting to output the predictions. We're seeing some blues. So far 100%, 94%. So it's 86, it's coming down. So it's predicting what Chris is doing with pretty high frequency, 88%. 89%. Keep going, Chris. You're doing really, really, really well. This is brilliant. Absolutely fantastic. So it's actually predicting with almost 90% accuracy how well Chris is able to be random. Remember, it should be 50%. So Chris is managing to lower it a bit now by mixing it up. But yeah, it's bottoming out around 70, 75% maybe. Okay, so thanks, Chris. That was brilliant. Thank you so much. Can we give Chris another round of applause? Brilliant. Thanks, Chris. Thank you so much. So this is interesting, right? Because it shows that we're not really very good at being random. If Chris was able to press those two keys purely at random, then it shouldn't be able to do any better than 50%. And actually, it's quite interesting, I think. We think that well-spaced, I said well-spaced is what we think of as random. In the case of just these two, we think F followed by D, F followed by D, alternating is sort of random. Although we know it's not quite random, so we throw a couple of double Fs and a couple of double Ds and then triple Fs and triple Ds, but we don't get that far. In the space of 100 keystrokes, if we were genuinely being random, if I was just tossing a coin to generate randomness, you would expect to have 5 consecutive Fs or 5 consecutive Ds at least once with a 95% probability. Okay, but that doesn't feel randomness. 5 Ds in a row doesn't feel very random. And actually what the computer's doing under the hood there is actually just counting our last 5 moves and keeping track of how often we've used those moves. And once you've done 4 key presses, it says what's the next most likely one based on this histogram of frequencies of the last 5 moves that we've done. So the computer is able, with a really simple algorithm, to predict what we're going to do. And actually, for me, I was worried because I was like, does this impinge on my free will? Am I not able to be random? Is the computer able to predict what I'm going to do? And it's a little bit worrying that we could be exploited by people if we're not able to be random, if we're not able to genuinely exert our free will. But that's maybe a little bit over the top. So we're not very good at being random, and the reasons are we think of randomness as being evenly spaced and often without clusters. Okay, so we don't think that 5 Fs or 5 Ds in a row is very random, but it is. It should happen, if you've pressed the keys 100 times, it should happen 95% of the time that you do that. We know completely regular spacing isn't random, though, so we tend to throw in a few double Fs, triple Fs, and whatever. And we also tend to exhibit middle bias. So you can't see it in that example, but there's another place where people try to be random but are not very good at it, and that's in the National Lottery. Okay, so in the UK, the National Lottery has been running since 1994. And on the 14th of January 1995, I think it was just the 13th draw, the jackpot had rolled over for a couple of weeks. People hadn't won for 2 weeks in a row. The jackpot had reached over £16 million. So lots of people were like, well, there's only 14 million different combinations. If I buy them all, that's not a good idea, though, right? Because if you split the jackpot, you are screwed, okay? So actually, though, 70 million tickets were sold. So some people were definitely buying more than one ticket because there aren't 70 million people in the United Kingdom. The numbers that came up were 7, 17, 23, 32, 38, and 42. So with 70 million tickets sold, the odds against winning the jackpot are 1 in 14 million. There's 14 different million combinations that come up. So you'd probably expect 5, maybe 6, maybe 4 winners of the jackpot on average. On the 14th of January 1995, there were 133 people that won the jackpot. Can you imagine that? 70 million jackpot. Yes, I've won 70 million. Oh, actually, I've won £100,000, so I've got to split it 133 ways. Can you imagine how devastated you would be? So it's not good news. But what I want to say to you is that I can't tell you how to win the lottery, but what I can tell you is that if you do win the lottery, I can give you a way to keep most of the jackpot and not share it with other people. So let's have a look at where these numbers sit. This is the National Lottery payslip as it was then. 49 balls, 6 numbers get chosen, so you get to choose 6 off here. So in the draw on the 14th of January 1995, this is where those winning numbers lay. Can you see now? This is why we're not good at being random. There's middle bias. They're not using the outer 2 columns at all. In fact, they're not even using the 4th column at all, right? They're using 2 columns. The numbers are quite evenly spaced, okay? There's a gap, then a number, gap, then a number, then a number, then a gap, then a number, then a number, and a number. So they're quite evenly spaced, but we know that really regularly spaced isn't random, right? So they've thrown one number to the side once or twice, and they've mixed it up a little bit. But actually, There's no clusters, no consecutive numbers in there at all, because we think clusters, consecutive numbers are not random, but in half of all these National Lottery draws, you would expect to see 2 consecutive numbers. And the other thing that really stymied this one was the number 7, the world's favourite number. So many people choose 7 for their lottery pick. Okay, so maybe this is just chance that these numbers exhibit this sort of pattern that I described before. Well, here's another one, 16th of March 1996, 57 people shared the jackpot. These are their numbers. Same pattern, right? Middle bias, the outer 2 are not being used, this time really evenly spaced. Okay, they've chosen 28, 38, and 48, which are really evenly spaced on this grid. So no number 7, but still exhibiting these patterns of really quite well spaced, no consecutive numbers. So, like I said, I can't tell you how to win the lottery, but I can help you to maximise your winnings if you do. So if you just play the National Lottery, the average return per pound that you would spend, this is when it was only £1 per ticket, is 45p. So you expect to lose 55p on average every time that you play. If you use a random number generator, which the National Lottery's lucky dip is just a random number generator, it picks the numbers randomly for you, you can increase your prize, your expected prize total, to a massive 55p. Okay, so it's not that much better. You're still losing 45p in the pound, but it's a little bit better, okay, so by using a random number. But what you really want to do to increase your expected winnings is to choose numbers that other people aren't going to choose. So exploit other people's perceptions of what randomness looks like in order to make sure that if you do win, you're the only person that wins. So pick unpopular sets of numbers. Well, what sets are unpopular? Well, numbers which are above 12, because that is the number of months we have in the year, and above 31, because those are the number of days in a month, because people use anniversaries and birthdays as their picks. So if you choose numbers that are above 31, then you're already a head start. You're already away from those people who are using dates to pick their lottery numbers. Don't worry about picking consecutive numbers, because like I said, in half of all draws, you would expect to see 2 consecutive numbers come up. But so many people think that that doesn't feel random, so they don't do it, okay? But if you have 2 consecutive numbers and you do win, then you're going to share the jackpot with fewer people. And don't shy away from the edges of the playing slip. Don't be subject to middle bias. Use these outer columns. So this is a sort of a sensible choice. It doesn't look very random, does it? Like I've put all the numbers, well, I've put 4 out of the 6 numbers above 31. That's so I can avoid those dates. But actually, every single pick in the National Lottery is just as likely to come up as every other one. Even though this doesn't look very random, no one's going to be choosing these numbers. So if you do win, then you can get a larger slice of the prize. The real take-home message from this is, though, even if you choose unpopular sets of numbers like this, your take-home per pound is still only 95p. So you're not making a profit. Even if you choose numbers like this, you're always losing, because of course they siphon off a large amount of the money in the National Lottery for profits and for good causes as well. So it's very, very difficult to make a profit by playing the lottery. So really the take home is don't play the lottery, of course. But that's very boring, so sorry about that. Okay, the last bit of the talk that I want to get to is about changing your mind. Because actually, if we're not able to change our minds, if we're not able to look at new evidence, then we will be confounded in our predictions about the future. So I want to give you an example. You've just moved into a new neighbourhood, and your neighbours invited you around for a street party or a house party, let's say a house party, to meet some of the neighbours. And they come up to you and they say, oh, this is Paul. And just as they're about to tell you what Paul does for a living, there's a big crash from the room next door, and the neighbour has to run off and go and sort out whatever priceless vase has been knocked over and fix that. So they don't get to finish they do finish their sentence, but it was obscured by the crash. You thought it could have said mechanic, but they might have also said mathematician. And so you're going to try and judge based on your preconceptions, your stereotypes of Paul, what he is. Is he a mathematician or a mechanic? So this is Paul. He's quite shy. He's looking down at his feet. He's got his arms by his side. He's not looking you in the eye. So this is stereotypical mathematician. I can say that because I'm a mathematician. But you know that joke, right? Like, how do you know when you're talking to the extrovert at the mathematician's Christmas party? Well, he'll be the one looking at your shoes instead of his, right? So yeah, there's these stereotypes about mathematicians, but they are stereotypes to some degree for a reason. So the question is it more likely that Paul is a mathematician or a mechanic? So let's make some basic assumptions. Let's assume that 50% of mathematicians are shy and 10% of mechanics are shy. Now, these numbers are probably too high for both of these professions, but actually given the people that I know who are mathematicians, this is maybe not too far off the mark. So if we take a representative sample of mathematicians and mechanics, it would seem to suggest that shy mathematicians outnumber the shy mechanics by a factor of 5 to 1. So it's actually much more likely that Paul is a mathematician than a mechanic. Apart from the fact that I can see some people shaking their heads in the audience, and that's very good. Apart from the fact we've neglected a really huge piece of data, right? We've just reasoned from new evidence that we've seen Paul is shy, but we've forgotten the fact that there are way more mechanics in the country than there are mathematicians. There are about 250,000 mechanics in the country and only about 5,000 people who would call themselves a mathematician. So actually, even when you limit the number of mechanics by saying only 10% of them are shy, there's still probably 10 times as many mechanics as there are mathematicians. We've neglected our prior data, our prior information, what we probably know, that there are far more mechanics in the country than there are people who would call themselves mathematicians. There are about 50 times as many. So even after we've said there are only 10% of them are shy and there are 50% of the mathematicians are shy, there's still way more shy mechanics than there are mathematicians. So really, we should be saying that it's far more likely that Paul is a mechanic than a mathematician, although it goes against our preconceptions and our stereotypes of what mechanics and mathematicians might be like. So this is an example of what's called Bayes' theorem, and there's a precise mathematical statement of Bayes' theorem. I'm not going to give you that, but there are 3 key lessons that I draw in the book. No equations in the book. There's just 3 key lessons about Bayes' theorem which can help us reason better in life. And the first one is that new evidence isn't everything. We shouldn't completely neglect everything we know based on a new piece of information which attracts our attention. So the analogy that I'll give, I'm a big football fan, I'm a big Man City fan. Last season, we bought a striker called Erling Haaland from Borussia Dortmund. He had been banging in goals in the Bundesliga and the German league for fun. He'd been banging goals in the Champions League. He was absolutely brilliant. He came very highly rated. Everyone was very excited about him. Liverpool, who are our main rivals the season before, they just bought a new striker as well. He was called Darwin Núñez, less well known, less of a reputation, but still quite an exciting prospect. Liverpool, who won the FA Cup, played Man City, who won the Premier League, in the opening game of the next season, where these 2 strikers were on show in the Community Shield. It's the curtain raiser before the Premier League season starts. So these 2 teams played each other, and the 2 strikers were on show. Erling Haaland did not score. Darwin Núñez did score. And the pundits said, you know what, I don't think Erling Haaland's cut out for the Premier League. I know he's done it in Germany, but I really don't think he's very good. Darwin Núñez looks like a brilliant signing, though. He's going to bang in the goals for Liverpool. Liverpool will probably go on and win the Premier League. As it happened, Erling Haaland, as many of you will know, went on to break the Premier League goal-scoring record. He won the Golden Boot in the Champions League. He scored goals in the FA Cup. Man City went on to win the treble last season. And what the pundits had done is they'd forgotten all the prior information, and they'd taken one data point, this new information that he hadn't scored in one game, and said, actually, I don't think he's very good. And they'd not reasoned like Bayesians. They'd forgotten all their prior information. So that's one lesson. New evidence isn't everything. Another lesson is that you should change your opinion incrementally. Okay, so at the end of last season, Erling Haaland didn't score for 6 games. That doesn't detract from the fact he still had a really, really good season, but it should make us think that we need to update our opinion ever so slightly, that maybe he wasn't quite as good as he was before he went on that 6-game streak without scoring. And to take it to extremes, if he went every game next season without scoring, and we didn't update our opinion every time he didn't score a goal, if we ignored every new piece of information because we were quite confident he was a really good striker, he would have gone a whole season without scoring, and we'd still be saying he was the best striker in the Premier League. And that doesn't make any sense. And then at the end of the season, we'd suddenly have to radically alter our opinion, which is where you get these accusations of sort of flip-flopping and U-turning in politicians, because people are not updating their opinions incrementally. They're doing it at the end of the season, if you like, when all the data's in, but you really, every time a new piece of information comes in, if Erling Haaland scores, that should improve your opinion of him, but if he doesn't score, it should slightly decrease your opinion of how good a striker is. You have to commit to changing your opinion incrementally if you're going to reason like a Bayesian. And the last message from Bayes, and this is where I want to sort of circle back to the start, is that we need to consider different points of view. You should never let yourself be 100% certain of any opinion. You should never be 100% certain about anything, because if you do and new information comes in, you're honor bound to ignore that new information. Okay, you have to, because you're 100% certain. You have to foster some doubt, otherwise you can't change your mind. Okay, so when new evidence comes in, we should be able to change our opinion, but you can't do that if you're 100% certain. And this is where we get into trouble when we're arguing with people like anti-vaxxers or climate change denialists, because they're 100% certain that vaccines don't work or that climate change is not man-made. And you can present them all the evidence in the world, but they won't change their opinions because they're 100% certain. But that's not a scientific way to look at things. Actually, we need to be able to have some doubt about our opinions so that when new information comes in, we can change our mind. As the economist John Maynard Keynes says, when my data changes, I change my mind. Okay. So we need to be able to consider a different point of view. And the reason I want to circle back to the very start is that it might seem very certain when a teacher tells you you're not good at maths or you're not good at English, that that's the gospel truth, and you start to believe that inside yourself. But actually, what I want to say is to have some doubt about the teacher who has told you that you're not good at maths or that you're not good at English, and to be able to change your mind maybe later in life when you realise that actually maths can be fun and interesting and useful, and maybe you actually could do mathematics after all. Because if we didn't do that, then we wouldn't have geniuses like Albert Einstein. And so the last take-home messages from this bit of the talk are coincidences can be surprisingly likely, so don't jump to conclusions that aren't warranted. When you see a coincidence which seems interesting, when you see Jesus in a piece of toast, it isn't necessarily a sign from above. We're not very good at being random, we're not very good at spotting randomness, and we're not very good at actually being random. So when you need to be random, maybe divest that randomness to an external random number generator. Flip a coin, roll a dice, use a random number generator on a computer to pick your lottery numbers. And finally, be prepared to change your mind, because it's only when we accept that we have uncertainty, when we accept that we're not sure about things and are open to new evidence, that we can learn to accept, if not always expect, the unexpected. Thanks very much.